Alright, just Schweitzer, and let's add in a little bit on stoichiometry of gases. So stoichiometry is simply linear proportions, and with that estimating becomes a powerful tool. 1 mole of any gases, STP is 22.4 liters, so it's a pretty common thing they use. Same questions, a mole of zinc and a mole of HCl create hydrogen gas, estimate the volume of gas produced. Alright, so in this case, if I have, let me grab a pencil here. Okay, so if I have a mole of zinc and a mole of hydrochloric acid, so 1 mole of this and 1 mole of this, and this is going to be my limiting reactant. So I'm going to get, in this case, every 2 to 1 ratio for volume of product gas, which is this guy. So I'm only going to get half a mole. So since at STP it's 22.4 liters, I'm going to get 11.2 liters. And that's a pretty common multiple choice question. Alright, so another one. 2.6 grams of aluminum reacts with excess hydrochloric acid, producing aluminum chloride and hydrogen gas. Alright, attempt to estimate the volume of gas produced after solve using factor label. Now, one thing you might notice here is, okay, we need moles. What does 1 mole of aluminum weigh? How much does 1 mole weigh? So it's about 27 grams, or 6.9. So let's just change this to like 2.7 grams. Alright, get a little closer. That means I have 2.7 or 2.69 divided by 269, 26.9. I'm going to get about 0.1 moles. Okay, so that's what that's intended to be, just a 0.1 mole conversion, simple one. Okay, so now I know that I have this aluminum, so AlCl. Alright, so Al plus hydrogen gas will give me AlCl3 plus, it would be plus HCl, sorry about that, yields H2. Alright, so let's say I want to balance this thing. In this case I need 2 here, so we put a 2 here. I get 2 of those. It's not going to work here, so let's try and double this thing. 2 there gives me a 2 here, 2, 3, 6. So I need a 6 here and a 3 there. Okay, so now I got my proportion set up. And I know that this is my limiting reactant. So for every 2 of these, I get 3 of those. Okay. And I have 0.1 moles. Okay, so 0.1 times 3 divided by 2. And it's 0.3 divided by 2, so let's calculate this out. So 0.3 divided by 2. And I get about 0.15. Okay, so I'm going to get 0.15 liters, I should say moles. And then now I need to convert this over to liters. And you could estimate, but let's go ahead and do this. It would be 0.15 moles, and get rid of the moles and go to the liters. 1 mole is 22.4 liters, and I'm going to get that answer times 22.4 equals 3.36. 3.36, and it would be liters. Alright, there we go. So why does pressure increase or decrease as a reaction proceeds? This is kind of an important concept that they ask quite frequently, actually. So when you draw this thing, essentially, let's say we go 1 cycle through this process. Now they're going to say typically a caveat that assuming the temperature remains the same or goes back to the same. Because obviously raising your temperature is going to cause particles to travel faster, which therefore causes an increased pressure. But here I take 7 particles. Okay, let's call this guy this, and we'll call this guy that. So 1, 2, 2 of those reacts with 1, 2, 3, 4, 5. 7 total. I get how many of these? 4 of, let's call it this and this. So I got 1, 2, 3, 4, 1, 2. So what happens here is I essentially go from having 7 particles, add up all your gas particles on the side, and you have another thing here where you have 6 particles. So I'm going from 7 to 6, and because I have less particles, technically, in this combustion reaction, once I return back to a normal temperature, which is, this is a combustion reaction, so that's going to be taking some time, we would have less pressure. Less collisions with the inside container of the wall. Alright, there we go. Alright, so a student needs to prepare some carbon dioxide and tends to use the following reaction with calcium carbonate is strongly heated. So we have this thing where it decomposes to form these particles. The question concerns the size of the balloon needed to accept the gas. How large will the balloon be if 1.25 grams of calcium carbonate is used? The pressure of the carbon dioxide is to be about that, and the pressure is going to be that. Okay, so this is just going to be kind of a stoichiometry / Hibner question. That's the way a lot of them work out. So first things first, let's start working our way backwards. We got the balloon, and we're looking for the size of the container, it says. So how large will it be if 1.25 grams is used, okay? I'm looking for this liter. So in Hibner, that's PV equals nRT, and V equals nRT over P. So I have a lot of this stuff already. I have R, I have T, use that, 298. I'm going to use atmospheres, so well, let's use this guy, 740 torr, 740 torr, so this is going to be 62.4, and then I just need my moles. Okay, that's moles of carbon dioxide, not moles of this guy, but 1.25 grams, and grams to moles, and I'm going to jump from here to here because that's a linear relationship, and it's a 1-to-1 ratio. Then I'll get from the moles back to grams. So here's definitely our stoichiometry stuff here. Carbon dioxide is 44 grams per mole. I don't know this one, so let's add this one up. Calcium carbonate. Calcium's at 40, carbon's at 12, and this guy is 48. I think you add that up, we get 100 grams per mole. So 1 to 100. And let's just do our math here. We got 1.25 divided by 100 is 0.0125. And then times 44. Now this goes to grams. Oh, we don't want grams. Alright, so let's take that off of there. Let's just stop right here. 0.0125 is the moles. So it's a nice number we got there. And this is going to get dropped right into here. Okay, 0.0125. Let's do our math. Times 62.4 times 298 divided by 740 equals about 1.25 liters. And there you go. So that's a form of a stoichiometry problem with gases. Alright, student hypothesis. If any of the following statements is true, justify or nullify it. Alright, so John says, we got 2 grams of hydrogen and 1 gram of oxygen will give you 3 grams of water. Okay, this is a big no. Alright, you're not going to be able to use them all up and you'll have excess. You got to convert to, this is a mole ratio, not a mass ratio. 2 grams and 1 gram will give you 2 grams of water. No, this is definitely not true because no matter what, even if you use the 2 grams as a limiting reactant, then you get at least 2 grams of water, but it needs to be bigger than that. Okay, or if you use this is the limiting reactant. Right? So it's not possible. 2 liters and 1 liter will give you 3 liters of water. Okay, well, let's try this out here. So I have H2O plus O2 yields H2O. And balancing hotwise here, we're going to get 2, 1, 2. Now, unlike mass, we just can't use mass in this ice table. We can use everything else pretty much. So 2, 1, what do I get? Minus 2, minus 1, 0, 0, and I get 2. And therefore the answer is still no. I'm not going to get 3 liters, I'm going to get 2 liters of gas. And that is the ice table right there. Nice. Okay. Alright. At 127, an entire sample of 2 grams of I2 is observed to have vaporized. How does the mass of vessel 5 change at 127 compared to 27? So this thing vaporizes and forms these little molecules out there. It's a little AP problem here. And what's our answer here? Well, really, it should be the same. And we didn't really lose anything. Well, that's got to be B. Alright, so before reaction, after reaction. Okay, take a moment to give this one a try. So we got a reaction mixture between NO and O2 produces NO2. Okay, in a rigid container. And in this situation, it says the pressure inside the container is recorded using a pressure gauge. Which of the following statements correctly predicts the pressure as the reaction goes to completion at constant temperature? And explain pressure. So first of all, you got to write this thing out here. So NO plus O2 yields NO2. Is it balanced? I got 3 oxygens here. I only got 2 over there. So in this case, I got to reshuffle this a little bit. And let's go with 2 of these guys. And now I get 4. Okay. So I'm going to take 3 particles and produce 2 particles. So my pressure should go down. Pressure will increase, pressure decrease. Okay. Now pressure will decrease because there are fewer particles of the product than reactants. I think that looks pretty good. That's kind of what we did. Pressure will decrease because the product molecules have a lower average. Nope, not that. Same temperature. So B is the correct answer. Alright, in which flask do the molecules have the greatest average speed? Okay, and which flask contains a number of moles of gas? Which flask contains the greatest number of density? So this problem here, this page here, isn't really stoichiometry necessarily of gases. So we'll do this here, but might get shuffled around eventually as far as if we think that this is really what we're looking for here. Looks like this is our last little page here, so we'll add it in here. Maybe it gets deleted later, but we'll see. So good review nonetheless. So which flask do the molecules have the greatest speed? So we have a couple things here. Kinetic energy equals 1/2 mv squared. This is my temperature, it's average temperature, and this is my speed of the particles. So in this case, one has the greatest speed. They're all pretty close temperature-wise. Okay, so I'm going to go with temperature here. Alright. Highest temperatures, these 2. And then of these 2, because nitrogen has a lower mass, it's going to have a higher velocity. So B is the one that has the highest average speed. Which flask contains the smallest number of moles? I think I'm going to give an answer on this one here. There we go. Which flask contains the smallest number of moles? Alright, so they're all the same volume, so PV equals nRT. And I'm looking for moles. So PV over RT equals moles. All right. So in this case, I know that you could plug them in there very quickly and just get your answers. You just sub in a volume of, let's say, 1 for this guy. So you'll keep in mind that my temperatures are all relatively close when you flip them to Kelvin. So I don't think the temperature is really going to be a factor here. All right, it's very close, but the pressures are. That is, however, going to be a major factor. This guy here, let's say, for example, has both the same temperature, so 0.5 to 1. This guy's got 2 times as many particles as that one does, so that guy's out. These two are the same temperature, so this guy's got 4 times the pressure. This guy is out. And this one here, same thing. Well, it's got the same 1 atmosphere. This guy, if you had the same pressure temperatures, this guy would have twice as many. Temperature's very close. This guy's out. So this guy has to be the answer. You can plug numbers in to verify, but it's a proportions question here. All right. We only have the smallest number of particles. Yes, I was backwards. So this guy got the highest, but B has the smallest. Again, that goes right to pressure once again. So these two have the same pressure, but the higher temperature is going to cause that still to be less particles. Alright, and the last one is, which flask has the greatest density? Density means more mass. The answer is C. So this is the one that I originally calculated as having the most particles. And that's why it's got most particles with a heavier particle, meaning greater density per area. Thank you very much.